not constant, then you have to leave it as a variable and you'll have to take a derivative. Okay, if the bottom of the ladder is sliding away, we'll call the bottom the x. It is sliding away means it's going in that direction. That means x is getting bigger. From the wall at the rate of 3 feet per second. That means x is changing, therefore dx dt is 3 feet per second. How fast is the angle, theta, formed by the ladder and the ground? That means this angle here, that's my theta, ladder on the ground, okay, changing at the instant. So that means they want me to find d theta dt, okay, at the instant the bottom of the ladder is 12 feet from the wall, so when x is equal to 12 feet. All right. Any questions on setting this up? Probably that's the hardest thing. Just writing out all the information, finding out what is given. Now, once this is given, the second hardest thing is to figure out what do I do with this. So you have to come up with some kind of mathematical model. We're dealing with an angle and two sides, so that means it must be trig. So, what trig function deals with adjacent side and hypotenuse, cosine? Now notice some of you will make a mistake of putting the 12 in. You can't put the 12 in there. Why is it I cannot put the 12 in there? It's not constant. Okay? It's not constant. You can only put constants in. So therefore, cosine of theta is equal to adjacent, which is x, over hypotenuse, which is 13. Okay, that is the function we're going to use. Obviously, this we're going to take a derivative because it's a calculus class. That's what we do half of the year. Okay, the other half of the year we take antiderivatives. Okay, then we're going to multiply both sides by 13, which is cosine of theta is equal to x. You don't have to do that. I just like to do it that way. Okay, and when I take the derivative of this, I'm going to get 13 as my coefficient. Derivative of this, I have to use a chain rule. Derivative of cosine is, okay, so be negative sign is correct, times the derivative of theta, which is, very good. And then on the other side, I get dx dt. After you do that, just plug in all the information that you have. So this is negative 13 sine of theta, which I don't know what that is. D theta dt is what I'm trying to find. Okay, so I leave that alone. And dx dt is 3. Okay, I'm trying to find d theta dt. I can find that as long as I know what sine of theta is. That's when the 12 comes in. Okay? So, this is 12. At that instant, that is 12. So I have to find out what this is when this is 12, and that's 13. 5. Right? I'm assuming that is correct, right? All right, there you go. Pay attention in geometry class. Okay. All right, so 5, 12, 13. So this is sine means I have a negative 13. Sine is opposite over hypotenuse. Okay, that's d theta dt is equal to 3. 13s are going to cancel. So I get d theta dt is equal to 3 over negative 5. Or negative 3 over 5. So let's just move the negative sign to the top. Units. Tell me what units do I put in here? Huh? Nope. Nope. Huh? Nope. Nope. Radians per second. Radians? Unless there's a degree symbol somewhere here, we don't use degrees. Okay? And this is an angle, so therefore it's radians. Now you have to write a short sentence, okay? You have to say, the question was, okay, how fast is the angle formed in the ladder changing? The angle is changing at, why do you use the word changing rather than increasing, decreasing? Because you don't have to worry about changing any signs here, okay? You can say, the angle is changing at, you can write that down and finish with a short sentence, okay? I will take a point off if you don't finish with a short sentence. Okay. All right. All right, let's go to 2. Number 2. The water is poured in a conical reservoir in the shape of a cone. So conical reservoir is a cone. Looks like that. And it's 6 feet tall with a radius of 4 feet. Okay. And so the radius is 4 feet. And it is 6 feet tall. So the height of that cone happens to be 6 feet. Alright. And it says, suppose the water is poured into the reservoir at the constant rate of 3 cubic feet. Okay, it says 3 cubic feet per minute. What is this? Volume. How can you tell it's a volume? By the cubic. As soon as you see the cubic, you know it's volume. So this is dV dt. That is the change of the volume. How fast is the water level rising? That means we'll call that height. So they want me to find dH dt. Okay. When, at the instant, the depth is 2 feet. You could use D for depth, but we're going to use H. That way it's not that confusing. Okay. Alright. So we're finding dH dt. Okay, it deals with the volume of a cone. That means you need to know the formula for volume of a cone. Volume of a cone is pi over 3. H. Gotta have another unit, right? How many cones are in a cylinder? Right? Very good. Because this is really pi r squared h would just be a cylinder, right? Okay. And pi r squared is just a circle, and height is the number of cylinders you have. Okay. Now, before you do anything, and you got to stop, okay, pay attention to me. What are we doing down there? Are you paying attention to me? You're looking down there. Yeah. What's that? I'm doing that. All right. Now, I have a V, I have an R, and I have an H. Those are 3 variables. If I take the derivative of this as is, I'm going to get a dV dt, I'm going to get a dr dt, I'm going to get a dH dt. dV dt is good to go because I have that. dH dt is good to go because I'm finding that. If I get dr dt, I'm in trouble. Unless I have dr dt given to me someplace, I can't do it. So what that tells you is you need to get rid of the r in place and replace that. So we're going to go back to geometry and use similar triangles. If this is a random r and if this is a random h, what 4 is to 6 is going to be what r is to h. It's going to be proportional because these two are similar right triangles here. Okay? So when we reduce this, I'm going to get 2/3 and multiply by h. That's going to give me the r. I'm going to take that, I'm going to put it back in here. So I have a pi over 3 and I have a 2/3 h, quantity squared h. And if you clean this up a little bit, I'm going to get 4 pi on the top. I'm going to get 9 times 3, which is 27, and I'm going to get h cubed. Okay, I'm good to go. I'm going to take a derivative of this. Derivative of that is dV dt. When I take the derivative of this, the 3 comes to the front. The 3 will reduce that 27 to a 9, I get 4 pi over 9 h squared times dh dt, because I have to apply the chain rule. Okay, plug in everything we have right now. So dv dt happens to be 3. I have a 4 pi over 9. Okay, h happens to be 2 squared and times dh dt. Okay, 2 squared is 4. 4 times 4 is 16. Okay, and that gets flipped, so the 9 ends up on the top. Okay, so it'd be 27 over 16 pi. That is my dh dt. Okay, and this, I got to put the units in. If you're given units, you must always put the units in. So this will be in terms of feet, cubed, squared, or just single unit. Feet what? Single units, because this is the height. Okay, per minute, and then short sentence. Right, moving on to 3. Number 3, water is poured into, another conical reservoir. Shape of a cone. Okay, and this 4 pi, again, the same thing. The radius is 4. And then the height is 6. We can use a lot of the other stuff we found already. Suppose the water level is rising at a constant rate. So water levels rising at a constant rate means that dH dt is changing at 1/2 feet per minute. Okay. How fast is the water being poured in? So that means they want to know how fast the volume is changing. So they want me to find, okay, dV dt, how fast the water is coming in. At the instant, the depth is when h is equal to 2 feet. Okay, same thing all over again. Okay, volume is equal to pi thirds r squared h. Again, I need to get rid of the r. We found out from the last problem, r turned out to be what? Okay, 2 over 3h. That's quantity squared h, and that simplified to 4 over 4 pi over 27 h cubed. Alright, take the derivative of this. dV dt is equal to 4 pi over 9, okay, h squared dH dt. And when you plug in 2, that will turn into 16 pi over 9, okay. Now, what's my dH dt? 1/2. Alright, that reduces now to 8 pi over 9. And what are my units on this one? Feet cubed per minute. This is volume. These related rates are not that bad. Once you get the hang of it. Like I said, I promise you there'll be one related rate question for your response. Alright. A, revolving searchlight on an island 1 mile from the straight shoreline. Okay, here's the straight shoreline. Here's 1 mile from straight shoreline. Okay, so this is 1 mile. Okay, it turns at a rate, shoreline turns at the rate of 2 revolutions per minute, counterclockwise direction. So that means it's going in this direction here. Okay, and it's going 2 revolutions per minute. 1 revolution is 2 pi, so 2 revolutions means 4 pi. So that angle is changing. D theta dt is 4 pi per minute. Okay. Counterclockwise. How fast is the light beam traveling along the shoreline? That means this is the distance we're trying to find. So they want me to find how fast that is changing. Find dx dt. when, okay, when the beam makes an angle of 45 degrees to shoreline right here. That turns into 45 degrees. Okay, we don't like, we'll call that theta, okay, and we don't like degrees. We're going to change this into radians. So what's 45 degrees in radians? Because that's in radians, so you can't have degrees and radians mixed together. Okay, now here's my angle. This is the side, and this is the side I'm dealing with. What trig function? Because it's a trig function because it deals with an angle, tangent. So tangent of theta is equal to opposite over adjacent. Right, hey, you know what? I don't like this. I'm going to flip it. Okay? X is equal to what if I flip both sides? Cotangent. Okay, take the derivative of cotangent. So this is dx dt is equal to, chain rule here, what's the derivative of cotangent? Negative cosecant squared theta d theta dt. Alright, so do I know what d theta dt is? Yeah. Okay, so that happens to be 4 pi. Do I know what cosecant is? Well, when at pi thirds, cosecant is related to what trig function? Sine, right? What's sine of pi fourths? So that means cosecant will be 2 over rad 2. So this is going to be 2 over rad 2 squared. Okay, so the top turns into 4, bottom turns into 2, so that reduces to 2. Okay, 2 times 4 is going to give me 8, so negative 8 pi. And this is in terms of what? No. Huh? No. How you doing, Jessica? What's my units here? Miles per minute. This is the distance. It's not an angle. So dx dt. Even though you see a pi, it doesn't mean it's radians. Pi is just 3.14. It's just a decimal. Okay, so that's it. Now, does it make sense that the x is getting shorter here? Yeah, because it's negative. Okay, so that's good to go. So now, here comes the second part. How fast is the wrong problem. How fast is the light beam traveling along the shoreline at the instant the beam makes a 90-degree angle? Right here. So they want to know how fast it's going when it hits that point right there. So that means when theta is equal to pi over 2. So let's plug it in. Okay, what is sine of pi over 2? When you flip it, what are you going to get? 1. Okay, so dx dt turns into negative, okay, 1 squared times 4 pi, which is negative 4 pi, and this is miles per minute. Short sentence for both of these. Go ahead. All right, last one. Thank you. Okay, the diameter and the height of a right circular cylinder are found to be a certain instant to be 10 centimeters. So right circular cylinder, so we're going to draw a cylinder here. There's my right circular cylinder. Okay, and the diameter here is 10 centimeters. Okay, all right, so from here to here is 10 centimeters, and then the height of this is going to be 20 centimeters. Okay, if the diameter is increasing at the rate of 3 centimeters per second, so that means I have no choice. I have to go dt is equal to 3 centimeters per second. Okay. What change in height will keep the volume the constant? So they want me to find dH dt. So the volume is constant. Okay. So first of all, that means the volume can't change. Before we can find out what the volume is, well, what is the volume of this cylinder to begin with? Well, how do you find the volume of a cylinder? Pi r squared h. Okay, so the volume of this cylinder as is, it's going to be pi times 5 squared times 20, and which is 25 times 20, so it's going to be 500 pi. Okay, so that's my volume. So the volume has to stay constant. Volume cannot change. So because volume is 500 pi, I can just plug that into that equation as is. Okay, so 500 pi, because it's constant, is equal to pi r squared h. All right, how many variables do I have left I'm dealing with right now? 2, h and r. H is okay because I'm finding that. R is not okay because I don't have any dr dt anywhere. So I do have a dd dt, so I have to replace r with a d, so d is equal to 2r. So what's my r equal to? Okay, d over 2. So we're going to rewrite this equation as 500 pi is equal to pi times d over 2 squared h. And if you clean this up, I got a 500 pi is equal to pi d squared, all that over 4h. All right, let's clean this up some more. Let's get rid of the pi and the 4. Divide by pi. Pi is going to cancel out. And multiply by 4. 4 times 500 is 2,000 is equal to d squared h. Where are we going now? I thought that was over. Huh? Huh? You're leaving. Huh? Ever? Oh, the Sorensen was you went up to leave. What's that? It's none of your business. All right. Let's take the derivative of this. Shh. 0. I have to use a product rule here. Okay, first times 0 to the second plus second, okay, which is h, times 0 to the first, which is 2d dd dt. Okay, so this is 0. Alright, I need to plug in everything I can right now. Alright, dH dt I'm okay. I'm going to leave that alone. Plus, do I know what h is at this instant? I don't know what that is. The height is changing. Okay. Now, the volume has to be constant, okay? But the height is changing. I know what my dd dt is. What's my dd dt? That's 3. Okay? Alright, so I still have 2h and d and a d squared that I need to worry about. But they do give me this right there. Okay? So what is the, hang on a second. Diameter of the height by circumference found in circles. The diameter is increasing at the rate. Okay. What is the change in height? Ooh. Alright. So my volume is equal to 500 pi. It's pi over r squared h. So divide this by pi, I get 500 is equal to r squared h. But can I use what? I can't hear you. No, because at the instant, what's happening to the can is I got this volume here, okay? So the height is changing. So that's changing. So diameter is changing too, and the height is changing too. So that means the height is not going to be 20 at that instant. What's that? Because it's not going to be the same diameter, and it's not going to be the same height. Yeah, I think. Yeah. I don't know why. Yeah, you're right. Got it. I don't know why I'm getting confused here. All right, let's plug in the information that's given to us because they gave us that information. Okay, it's 0 is equal to d squared. My d happens to be 10. Okay, and then my dh dt is what I'm trying to find. Okay, and then plus 2 times h, which happens to be 20. Okay, times d, which is 10, and then times 3. Okay, so take everything to one side. Okay, that means take that over. That's 20 times 10 is 200 times 3, which is 600. 600 times 2, which is 1200 minus, and this is going to be 100. All that over 100 is equal to dh dt. And of course, this is going to be negative 12, and this is in terms of what? Centimeters per second, which is dh dt. Okay. That means if the volume stays the same, if the can gets flat, fatter, okay, my height is going to has to be changing to keep the volume the same. Does that make sense? The big can here, if I start squeezing it down, my height has to, change at this rate to keep my volume the same, which is 500 pi. So the statement is the height is changing at negative 12 centimeters per second. Okay. All right. That's it for section 14. So last section, section 15. Right. What would you like to see? What would you like to see? Okay. All right. You need to find vertical and horizontal asymptotes. In the past, I excused you from the vertical or the horizontal asymptotes, but now you're not going to be excused from that because you know how to take limits. First of all, I have a vertical asymptote. Where's my vertical asymptote? At x is equal to 2. Horizontal asymptote. You have to do some work. Okay, you got to check the limit as x, and this is the work you have to show. To positive infinity, okay, 4 over x, x minus 2. What's the limit of that? Limit as x goes to, you could have two different horizontal asymptotes, okay? It doesn't mean you're going to have the same horizontal asymptotes. If you remember tan inverse, okay, it looks like this, okay? And that's pi over 2 when you go to the right, and this is negative pi over 2 when you go to the left. So it could have two different horizontal asymptotes. Okay, so negative infinity, you got to check that also. This is also turns into, just so happens it is exactly the same. So horizontal asymptote is y is equal to 4. And this is your justification. Okay, number 2. F of x is equal to 1 over x squared plus 1. Vertical asymptote. Does this have any vertical asymptotes? No. Okay, so it's none. There's not a single number that I can't use. Horizontal asymptotes. Okay. Again, I have to show work. Limit as x goes to positive infinity. 1 over x squared plus 1. Okay, where's this going to go to? 0. Okay, limit as x goes to negative infinity. 1 over x squared plus 1. Where's this going to go to? 0. So I only have one, and that is y is equal to 0. All right, one more tricky one on this one. 3. I bet you, what'd you get for vertical asymptotes? Okay. What about your domain? Vertical asymptotes. What two numbers I can't have here? X is equal to what? 1, and x is equal to negative 1. Now, notice I wrote them separately. If you write x is equal to plus or minus 1, I'm going to take a point off. Because these are equations of a line. So you have to write them separately. Okay? Remember to do that. All right, horizontal asymptotes. Got to do some work. Limit as x goes to positive infinity of x over square root of x squared minus 1. Okay, I will have to multiply the bottom by 1 over x squared. Square root that because I have to go inside the radical. I'm going to multiply top by 1 over x. Because that's my highest power. It's the same thing right here, x squared, 1 over x squared, radical, and then 1 over x is the same thing. So when I simplify this, I get limit as x goes to positive infinity. Okay, I'm going to get 1 on the top, and on the bottom, I'm going to get 1 minus 1 over x squared. Okay, so when x goes to infinity, where is this thing going to go to? 0. So top's going to go to 1, bottom's going to go 1, this is going to go to 1. So I have 1, x, y is equal to 1. That is one of my horizontal asymptotes. Then I got to check what limit as x goes to negative infinity. fx over square root of x squared minus 1. And if you do the same thing, you would be wrong. What's wrong with this picture right now? Because this is not positive 1, this is really negative 1 because you're using negative numbers. So I put negative right there to adjust for that. Well, that negative goes outside. Then you have a limit as x goes to negative infinity of 1 over square root of a 1 minus 1 over x squared. That's going to 0. So where's this thing going to go to? Negative 1. So you have y is equal to